Hi. In this video, we are going to look at some advanced problems in number theory. So let's get started. This video will include problems that cover the concepts from the previous 4 videos. So hopefully you'll learn something from the questions that we discussed today. The first one is this one. If integers a and b satisfy the equation 2a square plus a is equal to 3b square plus b, then show that both a minus b and 2a plus 2b plus 1 are perfect squares. We have to prove that a minus b and 2a plus 2b plus 1 are both perfect squares if this condition is satisfied, right? So let's start by trying to simplify this equation a little bit. So we can say 2a square plus a is equal to 3b square plus b can be rearranged like this. You can take 2b square from the RHS into the LHS. So you get 2a square minus 2b square. And you can take a minus b here, and you are left with b square on the right side, right? So this can be factorized now. You can get a minus b common factor and 2a plus 2b plus 1. You are getting a minus b into 2a plus 2b plus 1 is equal to b square, right? Notice that this is good because we needed to prove something about a minus b and 2a plus 2b plus 1, right? Great. So first of all, you have to realize that this number 2a plus 2b plus 1 is odd, so it cannot be 0, right? Can't be 0 because it is an odd integer, right? Now, let's denote the GCD of a minus b and 2a plus 2b plus 1 as d. The GCD of a minus b and 2a plus 2b plus 1 is d. What we have to do first, the first step is proving that d is equal to 1. We'll first prove that d is equal to 1. So how do we do that? If d is greater than 1, right, then if this integer d is greater than 1, then d has a prime factor, right? Any integer greater than 1 has a prime factor, and let's call that prime factor p. If d is greater than 1, then d has a prime factor p. We know that p will divide b square. We know p divides b square. Why? Because d is the GCD of the left-hand side terms. So d definitely divides this and d divides this. And if you have a prime factor of d, which is p, then p also must divide this, right? Because from this equation, we can infer that d divides b square. Because the product of these two is equal to b square. So d divides b square. And if d has a prime factor p, then p divides b square, right? So if p divides b square, we know that p must divide b. And we already know that d divides a minus b because d is the GCD of a minus b and 2a plus 2b plus 1. So that we know p divides a minus b. If d divides a minus b, then p is a prime factor of d. So therefore, p also divides b a minus b. So we have p divides b and p divides a minus b, which together means that p divides a, right? So basically, p divides a is coming. And we also know that p divides 2a plus 2b plus 1. How do we know this? Because we, again, same argument. D is the divisor of 2a plus 2b plus 1. So P is the divisor of 2a plus 2b plus 1. But now we have a contradiction because we have already concluded that P divides B, P divides A. So P clearly divides 2a plus 2b. So how can I divide 2a plus 2b plus 1? Because that will mean that P divides 1, right? P divides 1 is a contradiction because P is a prime number. No prime number divides 1, right? So therefore, we have arrived at a contradiction by saying that D was greater than 1. So that means that D cannot be greater than 1, and that means that D must be equal to 1, right? Because the GCD is always positive. So if it cannot be greater than 1, it must be 1. That means A minus B and 2A plus 2B plus 1 are co-prime, right? So what we have concluded so far is A minus B into 2A plus 2B plus 1 is equal to B square. And we have just now found that A minus B, 2A plus 2B plus 1, GCD is 1. So these two numbers are co-prime. And if you recall, in a previous problem, in one of the previous classes, we had said that if there are two co-prime numbers and the product of those two numbers is kth power of something, some integer, then the numbers themselves are also kth powers of some integer, right? We had shown this in a previous class. So we are going to use that. We are going to say since product of A minus B and 2A plus 2B plus 1, which are two co-prime numbers, is the square of B, therefore A minus B and 2A plus 2B plus 1 must also be perfect squares, must also be the squares of some integers. The only thing you have to show here is that A minus B has to be positive. That is the only thing that is left to prove. We have already gotten our conclusion. A minus B has to be positive. That is what you need to show. So what we can say is, suppose A minus B is less than 0. So then we can say that, okay, B minus A must be positive. So B minus A can be written as R square in that case, right? So we have R square times 2A plus 2B plus 1 is equal to minus B square. This is my equation now. This equation implies that R divides B. Because this side we have R square, so this side also R must divide B, right? And if R divides B, and we already know that B minus A is R square, so R clearly divides B minus A also. R divides B minus A. So from there it follows that R must divide A. We have R divides B, R divides B minus A. Therefore, R must divide A, right? So we have the two things, R divides A and R divides B. So we can say A can be written as A1 times R, B can be written as B1 times R. And now we put this into the equation, into this equation, or in this equation. You can just put it here and take mod 3. So put it in the original equation. We had 2A plus 2B plus 1 is equal to B square. Put A is equal to A1R and B is equal to B1R in this equation and take modulo 3. What you should get is basically this condition, A1 square plus 6A1R plus 3R square plus 1 is equal to 0 mod 3. This is what you will get if you take all the terms on one side and simplify the terms a little bit, right? This means that since this is anyway 0 mod 3, this means A square plus 1 is 0 mod 3, right? But this is not possible because we know that the squares of integers are always either 0 or 1 mod 3. You can check all the squares of integers are always 0 or 1 mod 3. So therefore A square plus 1 will be either 1 or 2 mod 3. But that is a contradiction because here you are getting it as 0 mod 3. So that proves that B minus A is not positive, right? We had assumed all this while that A minus B is less than 0, right? this was our assumption, and we have arrived at a contradiction from here. So that means a minus b must be greater than 0. And since we have already shown that once a minus b and 2a plus 2b plus 1 are greater than 0, we have already shown that they are perfect squares. That part was already done. All we needed to show was the number is positive, right? Otherwise, it will not be a perfect square. So that concludes our proof. Right. Let's look at the next problem. Question number 2. We have proved that for any prime p, there exists a positive integer. There exists a positive integer n such that p divides 2 power n plus 3 power n plus 6 power n minus 1. Okay, so let's think about what we can do here. So for any prime p, we have to prove that. So let's check the simple cases, the first couple of primes. When p is equal to 2 and p is equal to 3, there exists a positive integer that this is divisible by 2 and divisible by 3, we have to show. So we can easily say that n is equal to 2 if I take, we will get 2 power 2 plus 3 power 2 plus 6 power 2 minus 1, which is basically 4 plus 9, 13 plus 36, 49 minus 1, 48. And it is clear that 2 divides 48 and 3 also divides 48. So for the first couple of cases, when p is a prime, p could be 2 or 3, we are easily being able to find an integer n such that p divides this expression, right? Now let p be greater than 3. Now we'll think of in general for primes larger than 3. We want to select n such that we can simplify basically 2 power n and 3 power n and 6 power n in a nice way. Only then we'll be able to say something about their divisibility, right? Now here is where we use Fermat's little theorem. So Fermat's little theorem says that if you have a prime p, then 2 power p minus 1 and 3 power p minus 1 and 6 power p minus 1 will be congruent to 1 mod p, right? 2 power p minus 1, 3 power p minus 1 and 6 power p minus 1 should be congruent to 1 mod p, right? So this was basically Fermat's theorem was a power p minus 1 is congruent to 1 mod p as long as a and p are coprime, right? If I remember correctly. So basically p should not divide a, right? So here we are assuming that p does not divide 2, 3 and 6. In that case, we would have 2 power p minus 1, 3 power p minus 1 and 6 power p minus 1 is 1 mod p. Now that's correct. Why is that correct? To p does not divide 2, 3 and 6 because we have taken p as greater than 3, right? And it's a prime number. So the lowest prime number is 5. 5 does not divide 2, 3 and 6. And after that, the numbers are 7 and 11 and 13. After that, the numbers themselves are bigger than this, right? So 7 does not divide 2, 3 and 6, right? So we are satisfying the conditions of Fermat's theorem because Fermat's theorem says that p should not divide a, and in that case, a power p minus 1 is congruent to 1 mod p, right? So because we are taking the case when p is greater than equal to 3, therefore we can say this, right? So if that is true, then what we get is 3 times 2 power p minus 1 plus 2 times 3 power p minus 1 plus 6 times 6 power p minus 1. If you think of this expression modulo p, right? So this is congruent to 1 mod p. So this 3 into 1. This is also congruent to 1 mod p. So this is also 1. And this is also congruent to 1 mod p. So this is overall congruent to 6 mod p. Right? So basically we have this expression 3 into 2 power p minus 1 plus 2 into 3 power p minus 1 plus 6 into p minus 1 congruent to 6 mod p. Right? Now, if I take 2 outside here, I can write that 6 into 2 power p minus 2. And I take 3 outside here, it will be 6 into 3 power p minus 2. And I take a 6 outside here, 6 into 6 power p minus 2 is congruent to 6 mod p. Right? And now we can divide by 6 and say that 2 power p minus 2 plus 3 power p minus 2 plus 6 power p minus 2 is congruent to 1 mod p. The reason we are able to divide by 6 is because we know p doesn't divide 6. That's why we can cancel 6 from this congruent, right? P and 6 are co-prime. That's why we are able to cancel. Otherwise, cancellation is not allowed. So we are getting this expression. So that means that 2 power p minus 2 plus 3 power p minus 2 plus 6 power p minus 2 minus 1 is congruent to 0 mod p, right? So we have found our value of n, right? Our n value is simply p minus 2, where p was greater than 3. P was a prime bigger than 3. You can take n as p minus 2 and you're getting 2 power n plus 3 power n plus 6 power n minus 1 is 0 mod p, right? So that completes our proof. Basically, we have shown that if you take primes larger than 3, then the power of n that satisfies this equation so that it is congruent to 0 mod p is p minus 2. And for primes lesser than 3 or primes equal to 3 or 2, n is equal to 2 simply fits, right? So basically the statement is now true in general. For any prime, that statement is basically proved. Okay, let's look at the next one. This question says that let a greater than 1 be an integer and set S be this set a square plus a minus 1, a cube plus a square minus 1, a power 4 plus a cube minus 1, and so on. You are constructing the set of integers like this. Prove that there exists an infinite subset in S in which the numbers are pairwise co-prime. So basically, you can see that the set S itself is an infinite set. You can see the pattern in the powers, a square plus a minus 1, then you add power 1 to each of the a terms, you get a cube plus a square minus 1, a power 4 plus a cube minus 1, and so on. So this can continue indefinitely. So the set S is itself an infinite set. Here a is greater than 1. We have to prove that there must be an infinite subset in S, in which all the numbers are pairwise co-prime. Basically, any two numbers that you select in that subset should have GCD 1, right? So the way we will do this is we will construct an infinite subset by induction. Construct an infinite subset T. Let's call it B1, B2, so on, of S by induction. So let's see how to go about that. So first of all, let B1 be equal to the first element in the subset. Let's use the first element of our original set S also, S, which is a square plus a minus 1. Let B1 be this. Now we prove that for all n greater than equal to 1, if we have already found if we have already found the numbers, B1, B2 till Bn in S, then we can always choose Bn plus 1 is equal to a power m plus 1 plus a power m minus 1 in the set S, which is co-prime with all of B1, B2 till Bn. So what is the logic here? We are saying that, let's say the first term in our infinite subset is B1, right? Now, what is the induction hypothesis? We assume that we are able to create a subset of n elements. The elements of the subset are B1 to Bn, and this is a subset such that all the elements here are pairwise co-prime. B1, B2, B2, B3, Bn, B1, all of these pairs are co-prime. So we have assumed that there is a subset with n elements which are co-prime to each other. The induction step is saying that we can always construct a new element in that subset. The new element will be a power m plus 1 plus a power m minus 1. That will be a part of this subset S. So that will be a part of the original set S, this new element. And this will become the next term in my subset T, such that this new term is co-prime with all of the existing terms. If the new element that we add to our subset is already co-prime with everything in the existing subset T, then the condition of the problem is satisfied. So as long as I can go and prove that taking a subset of n elements, I can construct a subset of n plus 1 elements. If this induction step is true, then automatically I can keep repeating the induction step for all n from 1 to infinity. And basically, our subset T will become an infinite subset satisfying the co-prime property, right? So basically, we have to figure out how to make this Bn plus 1, or what is the m, right? So Bn plus 1 is equal to a power m plus 1 plus a power m minus 1. Here m is a parameter that has to be determined. And it must depend on B1, B2 till Bn. We have already assumed that T set, which is B1, B2, Bn, satisfies the properties of the problem. So basically, all the elements here are pairwise co-prime. We need to prove that there is a Bn plus 1 that can be part of this subset, right? Okay, so since the numbers in S, what were the numbers in S? It was a square plus a minus 1, a cube plus a square minus 1, and so on, are all co-prime with A. Right? We have GCD of n and A equal to 1, where capital N is basically B1, B2 till Bn. Right? So we are saying that capital N is the product of the elements of this, and each of the numbers, correct. So each of these B1, B2 and all, right, they are B1 belongs to S, B2 belongs to S, and so on. And we can see from this pattern here, each of the BIs are such that they are co-prime with, or they have GCD with A is 1, right? They don't have any common factor because these numbers are all -1 mod A, right? So they don't have any common factors with A. So B1, B2, B are all co-prime with A. Therefore, the product will also be co-prime with A. So therefore, that is what we are saying. NA, the GCD is 1, right? If we pick M to be phi of N, here phi is the Euler's totient function, then from Euler's theorem, we know that A power phi of N is congruent to 1 mod N, right? A power phi of N is congruent to 1 mod N. That we have picked M as phi of N, right? And A power phi of N is congruent to 1 mod N. Therefore, we can say that A power M plus 1 plus A power M minus 1. This is my B of N plus 1, right? So this is becoming A power phi of N plus 1 plus A power phi of N minus 1, right? Now, if you think about this, this is congruent to A power phi of N. We know A power phi of N was congruent to 1 mod N, right? So therefore, this is congruent to A power phi of N times A plus A power phi of N minus 1. So this is congruent to A into 1 plus 1 minus 1, or congruent to A mod N. So we are getting B of N plus 1 is congruent to A mod N, right? Now, because GCD of A and N is equal to 1, right? That implies that A and N are co-prime with each other. So what we are getting is B of N plus 1 is coming out here as some N times K plus A, right? So what can we say about the GCD of B of N plus 1 and N, right? GCD of B of N plus 1 and N is equal to GCD of N and A, which is equal to 1. This is by Euler's division algorithm. GCD of N plus 1 and N should be equal to the GCD of N and A, which is equal to 1, right? So we are getting B of N plus 1 and N, GCD is 1. That means B of N plus 1 is co-prime with the product of the numbers B1, B2 till Bn. So if B of N plus 1 is co-prime with the product of the numbers, then it must be co-prime with each of the individual numbers, right? So basically we have shown that this number that we have selected, where M was equal to phi of N, where N was the product of all the numbers, B1, B2 till Bn, is satisfying the condition, and therefore we have been able to construct a subset of elements N plus 1 such that all the numbers are pairwise co-prime, right? So that completes our induction, and basically now we can keep repeating the induction step for infinite number of times, and you will eventually end up showing that it is an infinite subset now. Okay, let's look at the next problem. This says let P be an odd prime number, and we have to prove that summation of j is equal to 0 to P Cj multiplied by P plus j Cj is congruent to 2 power P plus 1 mod P square. Okay. So we have to show that this summation is congruent to this mod of P square, right? Okay, so note that for j goes from 0, 1 till P minus 1, what is P plus j Cj? P plus j Cj is simply this product, P plus j p plus j minus 1 till p plus 1 divided by j factorial, right? Correct. Now, p plus j cj mod p plus j cj mod p would be equal to, when you do mod p here, you are going to get j into j minus 1 and so on. So you'll get j into j minus 1 and so on till 1 by j factorial mod p. You take modulus on both sides, you are going to end up with j minus 1 and so on, right? This is what we are getting, which is congruent to 1 mod p. So you're getting p plus j cj mod p is congruent to 1 mod p, right? Now, we already know that PCJ is a multiple of P, when 0 is less than J is less than P. This is a pretty standard result. You can try to prove it yourself also. Expand PCJ and check whether it is a multiple of P or not. It is a fact. You should verify it yourself. So that means PCJ mod P is congruent to basically 0 mod P. PCJ is congruent to 0 mod P, and you can write PCJ as some K2 times P, right? Where K2 is an integer. And we already know that P plus JCJ is K1 P plus 1, right? So when you multiply these two things, you will get, why am I saying it is K1 P plus 1? Because it was 1 mod P. So K1 is an integer, K1 P plus 1 is the form of this, right? And we know that PCJ is a multiple of P, so it is K2P. So when you multiply these two things together, you should get something like this, K1P plus 1 multiplied by K2P. You're getting K1, K2P square plus K2P, right? And if you take mod P here, you are going to get K2P, right? Mod P square. If you take mod P square here, you're going to get K2P mod P square, which is same as PCJ mod P square, right? So what I'm saying here is P plus JCJ multiplied by PCJ is congruent to, we are getting something like this, K1P plus 1 into K2P, which is K1 K2P square plus K2P. So if I take modulus of P square on both sides, this is congruent to K2P mod P square, which is what? K2P was a representation for PCJ, right? So eventually we can say that P plus JCJ multiplied by PCJ is congruent to PCJ mod P square, right? You can check this by putting some arbitrary values of J and all, right? Now what we will do is the summation that we needed. We need to do the sum of this. Sum of J goes from 0 to P, PCJ, P plus JCJ. That is the same as J going from 0 to P minus 1 of, now I can say that this product is PCJ, right? If you are taking modulus of P square, using this result above, the product is PCJ mod P square. So I'm going to do the summation till P minus 1, because the last term, when J is equal to P, this becomes simply 2PCP, right? Because it is becoming PCP plus 2PCP, right? Great. So we are getting this mod P square is coming, right? And the value of this is what? This is the sum of J goes from 0 to P minus 1 PCJ. That is simply 2 power P minus 1 plus 2PCP mod P square. This is what we are getting. And when you do mod P square here, 2PCP, if you think about it, what is 2PCP mod P square? So 2PCP is equal to the sum of J goes from 0 to P, PCJ whole square, right? This is the standard identity. So this can be written as J goes from 1 to P minus 1, PCJ whole square. plus, which terms have I excluded? The 0 term and the p term. The 0 term, when j is 0, it will be 1. When the j is p, then in that case also it will be 1. So we're going to do a plus 2 here, right? So since we already know that PCJ is 0 mod p, so PCJ square should be 0 mod p square, right? That is obvious because PCJ is a multiple of p, so PCJ square will be multiple of p square. So overall, 2PCP is coming out to be 2 mod p square. So the overall summation is becoming 2 power p minus 1 plus 2 mod p square, and which is basically 2 power p plus 1 mod p square. This is what we wanted to prove, right? So that's the solution for this one. Let's go on to the next problem. This is question number 5. We are looking at a Diophantine equation now. Find all positive integer solutions to equation. The equation is this: x cubed plus y plus 1 is equal to x, y, z. We have to find positive integer solutions here, right? So let's rearrange the solution a little bit, in equation a little bit. X plus 1 is equal to x, y, z minus x cubed. So we can write it as x common y, z minus x squared, right? So what we will say, this is y plus 1 is equal to this thing. So let yz minus x squared is equal to n. And the equation will become xn is equal to y plus 1, right? Correct. And from here, we can say that x squared is equal to yz minus n. And that means x squared is equal to yz minus n. And we can say that what was y? Y was what? Y was xn minus 1. Let's put this y here in this. So we'll get x square is equal to, instead of y, you'll get xn minus 1 z minus n, right? So you're getting x square is equal to x zn minus z minus n. Basically, what have I achieved? I have eliminated y. That's what I have done. And I have gotten a new variable for n here. But what we know for sure here is that since x square is equal to xzn minus this, that means xzn is greater than x square. That means zn is greater than x, right? Zn is greater than x. So therefore, zn can be written as some x plus k, right? Because zn is greater than x, k must be greater than 0, right? Now we take this zn value and we put it back in the original equation, in this equation. So we will say x square is equal to x times zn, we will write as x plus k minus z minus n. We have taken zn is equal to x plus k from here and put it back in this equation. We are getting this. So notice here that x square is equal to x square plus kx minus z minus n. So x square is getting cancelled and we are getting z plus n is equal to kx. Z plus n is coming as kx. Now what do? I have two different equations which look so quite similar. I have z plus n is kx and zn is equal to x plus k. Adding the two equations, I get zn plus kx is equal to x plus k plus n plus z, right? Zn plus kx is x plus k plus n plus z. And now we can factorize this by taking terms on one side. We can zn minus n. Zn minus n minus z on one side. And I will take x plus k minus kx on one side. Here I can simplify it as z common n minus 1 and I have a minus n, how do I get a n minus 1 factor? I should do a plus 1 minus 1, right? Is equal to, I can write this as x common 1 minus k plus k minus 1 plus 1, right? I'm doing this minus 1 plus 1 and plus 1 minus 1 only to factorize it, right? So let me do it on top here. What you will end up getting is this. We are getting z minus 1, n minus 1, minus 1, right? Is equal to, on the other side, I will get k minus 1 into 1 minus x plus 1, right? Bringing the terms on one side, I'll get z minus 1, n minus 1, plus k minus 1, x minus 1 equal to 2. This is what we get, right? Now we know that k was a positive integer here. Z, n, x, everything is a positive integer, right? So the only way in which this can happen, are three cases. Case one is z minus 1, n minus 1 is 0, and k minus 1, x minus 1 is 2. Case 2 is this is 1, this is also 1. And finally, case 3 is when the first term is 2 and the second term is 0. Each of these cases can now be simply solved. When z minus 1, n minus 1 is 0 and k minus 1, x minus 1 is 2, we can take sub cases now and solve for both n, z, k, and x, right? When you do the solution, you will end up with multiple different ordered triplets of x, y, and z. So I will leave the final step of the solution to you. What I will just tell you are the different triplets that satisfy this. So xyz could be 215, 291, 325, 314, 113, 122, 593, 232, and 514, 2. These are the different triplets, I think, that I have gotten which satisfy this relation. So I'm leaving the final few steps to you. Notice the first part of the problem is the main thing. So if you have gotten that, I think you will be able to solve this problem. Let's look at the final problem for today's session. This is the fifth one. Let's say let n be an integer, be a given odd integer, then the equation x square plus n power a is equal to 4 power b has at most a finite number of positive integer solutions a, b, and x. We have to prove that the equation has only a maximum of a finite number of positive integer solutions for a, b, and x. We are given that n is an odd integer, right? N is a given odd integer. Now, what are the things that we can conclude immediately? The first thing we can conclude is x must be odd. X must be odd. Also, a must be odd. Why? Think about it. If x is even, what will happen? Right? X is even. So let's say x is equal to 2k. So you will get 4k square plus n power a is equal to 4 power b, but n is odd. If n is odd, this number is odd, and this is even, and this is even, right? So that is not possible. So by parity, we have figured out that x cannot be 2k, x must be odd, right? Similarly, you can also figure out that a must be odd, right? Why should a be odd? Think about it. Uh, let's say a is even. X square plus n power 2k is equal to 4 power b. We know that x is odd, so it is 2k plus 1 square, not 2k plus 1. Let's say it is 2l plus 1 square. 2l plus 1 square plus n power 2k is equal to 4 power b, right? So n is an odd number, we know, right? So if you think about this, this is going to be 1 mod 4, right? And n is an odd number, so the square of it is going to be also odd. So it can be, it cannot be 2 mod 4, right? It can be 1 mod 4 or 3 mod 4, right? N power a, right? Actually, it can only be 1 mod 4. Why? Because we are assuming that a is even, but k is odd, right? A is equal to 2 into k, and we are saying k is odd. In that case, an odd number to the power of 2k, right? So we can say that that is what? N power k whole square, right? And n power k is odd to the power odd. So that will be 1 mod 4, right? 1 mod 4 square will also be 1 mod 4. You are going to eventually get left hand side is 2 mod 4, but right hand side is 0 mod 4, right? Correct. So for example, if I take 3 power 6, 3 power 6 is 729. So notice that 729 is 1 mod 4, right? Take even numbers where k is odd, right? In that case, you will always find this as 1 mod 4. So you are going to get a contradiction, and you are going to be able to show that x and a both must be odd, right? So we have 3 things so far. X is odd, a is odd, n is odd, right? That was given in the question itself. Great. So now we can rewrite n power a as 4 power b minus x square, and 4 power b is 2 power 2b minus x square. So we can rewrite that as 2 power b minus x and 2 power b plus x, right? That is n power a. So we are getting n power a is the product of these two numbers. And now we'll analyze this a little bit. N power a is equal to 2 power b minus x and 2 power b plus x. And let's say that d is the GCD of 2 power b minus x and 2 power b plus x. D is the HCF or GCD of this. So that means from here we can say that d divides 2 power b minus x and d divides 2 power b plus x. So that implies that d divides the sum of these two, right? D divides the sum of these two numbers. So that means that d divides 2 power b plus 1, right? So that implies what? If d divides 2 power b plus 1, d is a power of 2. We get that. D is a power of 2, right? Also, we can say from here, d divides 2 power b plus x minus 2 power b minus x. So that implies d divides 2x, right? If d divides 2x and we know that x is odd, right? So that would mean x is odd, d divides 2x. So that would mean since d is a power of 2, we have to have d is either 2 power 0 or 2 power 1, right? Correct? Because this side is 0 mod 2. So d, since it is a power of 2, it cannot be higher powers of 2, right? D cannot be 2 square. Why? Because if it was 2 square does not divide 2 power x if 2 is odd. Because on this side, the power of 2 is only 1. The maximum power of 2 in the prime factorization of 2x is simply 1. So d must be 2 power 0 or 2 power 1, right? Great. So basically d can be 1 or 2. This is what we have concluded so far. Now we know that 2 power b minus x is odd. Why do we know that? Because 2 power b is even, but x is odd. So the subtraction of even minus odd must be odd, right? So if 2 power b minus x is odd and d divides 2 power b minus x, and d can be only 1 or 2, so how can it divide an odd number? 2 cannot divide an odd number, right? So d must be 1, right? We are concluding since d is 1 or 2 and 2 power b minus x is odd, d has to divide it, so d must be 1, right? So from here, what we have figured out from this argument is that 2 power b minus x and 2 power b plus x are co-prime. Their GCD is 1, right? Now we use the same property that we have used earlier today as well, and in a previous class we had proved this. So we are getting this, and we are saying that the product of two co-prime numbers, which are the two co-prime numbers, 2 power b minus x and 2 power b plus x, is the eighth power of an integer. So that implies that the numbers 2 power b minus x and 2 power b plus x must also be the eighth powers of some integers. Eighth powers of some integers. This property I have proved in a previous class, and we are going to use that now. So we are going to say that let's say 2 power b minus x is u power a, and 2 power b plus x is b power a, right? Now we are getting 2 power b minus x multiplied by 2 power b plus x is equal to u v power a is equal to n power a, which implies uv is equal to n. This relation we are getting, uv is equal to n, and we also have u power a plus v power a. If you add these two, you are getting it is equal to 2 power b plus 1, right? And when we add this, we know that a is odd. We had already decided that in the beginning. A is odd, so u power a plus v power a can be factorized like this. U plus v, u power a minus 1 plus u power a minus 2v, and so on, with alternating signs. So it will be u power a minus 1 minus u power a minus 2v, and so on, with alternating signs. And finally, v power a minus 1 is equal to 2 power b plus 1, right? So now what we can say here is the product of this and this expression is equal to 2 power b plus 1. So we get, I will just rewrite it a little bit. We have uv is equal to n, and we have u plus v multiplied by u power a minus 1 minus u power a minus 2v plus minus uv a minus 2 plus v power a minus 1 is equal to 2 power b plus 1, right? So since we know that n is odd, this implies that u and v are odd, are both odd, right? U and v are both odd. So what we have here, when we think of this now, you should realize that this is an odd number of odd integers that are being added or subtracted. You can count a was odd, so a minus 1 is even. So you will realize that there are an odd number of integers here, right? You can think about it, 0 to a minus 1 powers for this. So there are a integers, a terms here, which are odd number of odd integers, right? So the if you have odd number of odd integers, what is the sum or difference of them going to be? It is going to be odd, has to be odd, right? So basically, the power of 2 present in this factor, since it is an odd number, it is 2 power 0, right? And since this is an even number, u and v were odd, and this is an sum of the two odd numbers is even. So this is an even number. So this must contain all the powers of 2, right? The only way the product of these two is going to be equal to 2 power b plus 1 is if this one was 1 and this one is 2 power b plus 1, right? So basically, we have u plus v is equal to 2 power b plus 1. And if you notice earlier, we had written this equation, u power a plus v power a is equal to 2 power b plus 1, right? That was the initial equation which we factorized. This implies clearly that a is 1, right? And now a is 1 we have already gotten, right? And we have this equation also, uv is equal to n, right? So we see that u and v have only a finite number of solutions. Here. Why? Because n is a positive integer. It can be expressed as a product of two different odd numbers only in a finite number of ways, right? Because n has a finite number of divisors. Since n has a finite number of divisors, you cannot do product of divisors in more than finite number of ways, right? So we know from here u plus v is equal to 2 power b plus 1. This equation was there for us, and we know that u and v ordered pair is only finite number of ordered pairs, right? So that implies that b also has only a finite number of possible values. We already know a is 1. We know that b has finite number of solutions. And now we can easily find x also because we had these equations in the beginning. These were the equations in the beginning. So from these two equations, since we know a and b, we can find x. And since b is finite number of solutions, we have basically proven that all three a, b, and x, there are only finite number of ordered pairs which satisfy it, right? So basically that concludes our proof, and we have used quite a few techniques. The standard technique is to prove that GCD is of the two numbers was 1, so they were co-prime, and we use the property that product of two co-prime integers being a power of some integer means the integers themselves are also those powers of some other integers. So that property I have used in 2 problems today. Hopefully, you can go back to the previous video and see the proof of that property, right? And you've learned something from this video, hopefully. And the next video that we'll be making for number theory will cover the topics of Chinese remainder theorem. And that will be a more theoretical video. So stay tuned for that one. And after that, we have another video on basically indeterminate equations part 2. So that will conclude our number theory section. So that's it for now. I'll see you next time.